Hello everyone, this is homework 24, the greatest common factor. So in this unit we look at factoring, and factoring is basically just the reverse of multiplication. For example, we know 5 times 3 is 15, so 15 is our product, and the 5 and the 3 are both factors. Here's an algebraic example. The 5x and the binomial quantity, so the whole thing, 2x plus 3. Those are the factors. And then this binomial is the product. And of course, from the last unit, we know that we could obtain this product by just distributing the 5x, because 5x times 2x would give us 10x squared. If we want to show the distribution, and 5x times 3 gives us the 15x. So basically what we're going to do is reverse this process. And here's the interesting one where we have a situation where typically we would FOIL this out, and the x minus 5 and the x plus 3 is binomial quantities, are the factors, and then this trinomial is our product. So we're going to look at reversing the situation, and the first thing to consider is what's called the greatest common factor. And if we're talking about the greatest common factor between two or more numbers, it's the largest number, that's why we call it the greatest, that divides evenly into the given numbers. So in a sense, it's going to be smaller than each of the given numbers, because it's the largest number that divides evenly into each of the numbers. Now there's two ways to go about finding the greatest common factor between two or more numbers. You could list a factor tree, or by listing the factors, so there's a more expedient way. But by the factor tree, here's what we mean. There's actually a theorem, fundamental theorem of, well, not of algebra, but any number can be written as a unique factor, a unique product of prime numbers. For example, no matter how you break up 18, 3 times 6 or 2 times 9, you're ultimately going to get to the same place. That is, if you chose 2 times 9, then 2 is prime, but you could break down 9 to be 3 times 3. And 3 are both prime. And just to show on a scrap paper here that no matter how you approached it, you'd get to the same result. What if somebody chose 3 times 6 instead of 2 times 9? Well, the 3 is prime, but then the 6 can be broken down to be 2 times 3. And you can see we have the exact same factors, 2 factors of 3 and 1 factor of 2. So that's the prime factorization. And then we could do that for 42 as well. Just pick 2 numbers that multiply to give 42, and it would be 6 and 7, I guess. Now 7 is prime, so we're done with that, but 6 can be broken down to be 2 times 3. So then the greatest common factor is going to be the product of all the common factors between the two numbers. So the 2 is common in the prime factorization, and 1 factor of 3 is common. So therefore the greatest common factor is 2 times 3, or 6. Now, that process can be exhaustive, especially if the numbers are large. Typically, when I'd be dealing with fairly small numbers, but here's another method. We could actually list the factors of each number, and then the largest factor that's common to both would be the greatest common factor. So, let's say here's the factors of 18. Well, we know 1 times 18, you always have to include 1 times the number itself. Okay, and then just work your way up or down, however you want to look at it. But go to the next number that divides evenly into 18, that's 2 and 9. And then 3 goes into 18 6 times, so 3 times 6. And that's going to be it, because 4 doesn't go into 18, 5 doesn't go into 18, and then you're back to 6, so you're kind of working your way around, right? So those are the factors of 18. And the factors of 42. You can list them any way you like, but I just think it's easiest just to do this. Work downwards and just start with 1, then go to a 2 if possible. Yep, 2 times 21. Is 3 possible? Yes, 3 times 14. If you have to, use your calculator. 4 does not divide evenly. 5 does not divide evenly into 42. 6 goes into 42 7 times, so 6 times 7 are factors. And that's it. So therefore, if you look amongst the list, the largest number that's common in those two lists is what we call the greatest common factor. And you can see that that's 6. So probably a little bit easier to do this, but then to make it even more streamlined, consider the following. Just list the factors of the smallest number, and then the largest factor that divides evenly into the other numbers is going to be the greatest common factor. Because see, what you could do here is you could list the factors of 18 like we did, and then ask, does 18 divide into 42? And it doesn't. I mean, you could use your calculator for that if you wanted to literally just say, 42 divided by 18 if you get a whole number. Nope, so it doesn't work. So you just continue, you start with the largest and you work your way down. And the first one you come across that divides evenly into the larger number is going to be the greatest common factor. So 18 does not divide into 42, 9 does not, but 6 does. So immediately we say 6 is the greatest common factor. See, it shortens things up, because what you could do is you could say the factors of 12. Okay, so we're going to list the factors of the smallest number. Okay, so that's 1 times 12. Two times 6, 3 times 4, and that's it. And then we start with the largest of these factors and we work our way down. And the first one that we come across that divides evenly, in this case into 30, would be the greatest common factor. So does 12 divide into 30 evenly? Nope. Does 6 divide into 30 evenly? Yes. So therefore, the greatest common factor is 6. So that's the way I would suggest. And when you do this enough, especially when the numbers are small, it's really rather easy to pick out the greatest common factor. But here I'll list the factors of 9. Well, I don't have much of a choice. Just 1 and 9, or 3 and 3. And so then the questions start with the largest. Does 9 divide into 63 evenly? And it does, 7 times. So the greatest common factor turns out to be 9. Between 30 and 42, we'll list the factors of 30. 1 times 30, 2 and 15, 3 and 10 work. Okay, 4 doesn't go into 30, but 5 goes into 36 times. Okay, and that's as far as we need to go, because otherwise we'd just be reversing these, and multiplication is commutative, you can reverse them. And so we start with the larger. Does 30 divide into 42 evenly? Nope. Does 50 divide into 42 evenly? No. Does 10 divide into 42 evenly? No. Does 6 divide into 42 evenly? Yes. 6 times 7 is 42. So the greatest common factor is 6 again. Alright, and then finally between three numbers. Again, you just list the factors of the smallest. So the factors of 18, which are 1 and 18, 2 and 9, 3 and 6. Let's see, 4 doesn't, not a factor of 18, 5 is not, 6 is, so again, this exhausts the list. And so we start with the larger, but now we have to check both. 18 does divide into 36 evenly, but it does not divide into 42. So then 9 goes into 36 evenly, but 9 doesn't divide into 42. And then 6 goes into 36 evenly, and 6 goes into 42 evenly as well. So the greatest common factor is 6 again. Alright, so we're going to see that as long as you know your multiplication facts, it's pretty easy to pick out the greatest common factor. But first off, the greatest common factor between variables. When you have variables involved, this is one of the easiest things out there. The greatest common factor is the variable that's raised to the smallest exponent. So immediately by inspection, you could pick out the greatest common factor for variable terms. Smallest exponent, x cubed. And that, of course, is because if you were to write x to the fifth, you don't have to write this down, I'm just making a point. In expanded form, it's really 5 factors of x, and x cubed is 3 factors of x. So you're looking for how many are common, and that's obviously 3 of them. So that's why we choose the least exponent. So it doesn't matter how many terms you have. Greatest common factor between the variables is the smallest power again, smallest exponent. So y cubed in this case. Right, between 45 and 63. See, a lot of these you can, just by knowing your multiplication facts, you don't have to go through the formal greatest common factor process like we did on the first page. You could just simply pick out the greatest common factor. When you look at 45 and 63, just knowing your multiplication facts, hopefully realize that 9 is common. And then between y to the 4th and y squared, the smallest power, y squared. When you have negatives involved, it's typically best to include the negative as part of the greatest common factor. So between negative 14 and 21, obviously 7 is common, but I'm going to include the negative. So negative 7, and then between x to the 5th and x to the 7th, smallest power, x to the 5th. Okay, so now we want a procedure for how to actually factor the greatest common factor from an algebraic expression. So here's a little method. We're going to have an easier method in a moment, but I'm going to show the formal method first. You determine the greatest common factor, as we had done in these problems here, and then we write each term as the product of the greatest common factor and whatever's left over to give us that term. And then we're going to use the distributive property in reverse. So recall the distributive property a times b plus c is equal to a times b plus a times c. We're going to reverse that. As long as we have an a that's common to the two terms, we're going to factor that out, because the a and is a factor and the b plus c is a factor. That gives us this product. So we're going to use the distributive property in reverse. Okay, so first the greatest common factor. Okay, between 7 and 28, 7. And between x to the 5th and x cubed, smallest power, x cubed. So then we rewrite this as the greatest common factor times whatever is necessary to give us that term. So if we have 7x cubed, we would multiply by x squared to get 7x to the 5th. And similarly, to get 28 and similarly we have the 7x cubed, and now we want to determine what is it when multiplied by 7x cubed gives us 28x cubed. Well, to get 28 from 7, we'd have to multiply by a 4, and it turns out we don't need a factor of x because it's already x cubed. So then, here's the distributive property in reverse. That a, this 7x cubed here, is common, and it's behaving as the a. So what we do is we write that down, and then in parentheses, the two terms, and you can cover up the 7x cubed if you wanted to, but you're going to write out the two terms in parentheses, x squared plus 4. And you could verify by distribution by using the distributive property that here we get 7x to the 5th, and then here we get 28x cubed. So here's an easier method. Instead of taking this middle step, just simply determine the greatest common factor, and then think of reversing the distributive property through multiplication. So between 5x and 15, my greatest common factor is 5. So just simply write down the 5, open up a set of parentheses. Now, one thing is that we're going to have as many terms in the set of parentheses as there are in the original expression. So there's going to be two terms here. And we're basically just reversing the distributive property. We're saying 5 times what is going to give us 5x. And that would just be an x. And then we say 5 times what is going to give us negative 15. And that would be a negative 3. Now, I like to think of it as reversing multiplication. Some people will think of it as division. They might say, okay, 5 divides into 5x how many times? And that would give us the x. And then 5 divides into negative 15 how many times? And that would give us the negative 3. So either way, the answer here, I'm just going to recopy it, is 5 times the binomial x minus 3. And you could check by distribution. Okay, so greatest common factor between 6x and 21 is 3. I'm going to write down 3. I know there's two terms in the parentheses here. To give me the first term, I ask 3 times what is going to give me 6x, and that's going to need a 2 and an x. And then to get the second term, 3 times what gives 21, and that would be positive 7. So again, I'll recopy the answer, and you can check with the distributive property. So it's your choice. Think about it as division again. You could say 3 goes into 6x how many times, and that's 2x, and then 3 goes into 21 how many times, and that would be your 7. Okay, now to some variable terms. Okay, greatest common factor here is smallest exponent, x to the 4th. So I write down the greatest common factor, open up a set of parentheses, reverse the distributive property through multiplication, and ask x to the fourth times what gives x to the fifth. There will be x to the first. You don't need to write the 1 in there, but if you want to, that's fine. And then x to the fourth times what is going to give negative 9x to the fourth, and all we need is the negative 9. So this would be x to the fourth times the binomial x minus 9. And once again, notice how you're going to have as many terms in parentheses here as you have in the original expression. 2 terms, 2 terms, 2 terms, 2 terms, 2 terms, 2 terms. Alright, here's one with coefficients and variables. Greatest common factor between 9 and 12 is 3. And between y to the fifth and y squared would be y squared. Smallest exponent again. And so then we write down that greatest common factor, 3y squared, open up a set of parentheses, and reverse the distributive property. So again, we ask 3y squared times what gives 9y to the fifth. Well, to get a 9, I need a 3. It looks like I need 3 more factors of y. And then we have minus, and the 3y squared times what gives us 12y squared, and all we're going to need is a 4, because the y squared is already there. So here's the answer rewritten. Okay, here's a trinomial. But you can see that not every term has an x, so the only thing we look for is the coefficients of the terms, and the greatest common factor is just simply 2. See, it's usually pretty easy. You don't have to go through that process, like I said, of the greatest common factor, because the numbers aren't typically going to be large. Okay, so if I pull the 2 out, okay, now I know I'm going to have 3 terms in this set of parentheses. And if I multiply, again, you could think of it as division or multiplication, but I like to think of reversing multiplication. 2 times what is going to give me a 4x squared? Well, I need a 2 and the x squared. 2 times what is going to give me the 2x? I need the plus and a 1x. I don't need to write the 1, of course. And then 2 times what is going to give me the negative 6. You basically, when you factor, as long as you don't factor a negative, just carry the sign down and then ask 2 times what gives 6, in this case 3. And so the correct factorization, I'll just recopy. And again, you don't need the 1 in front of the x. Okay, here's one a little more interesting. But just compare the terms factor by factor. Compare the coefficients, 35, 25, and 40. And looks like a 5 would be common. And then compare the variable. And the variables, again, the smallest power, in this case x cubed. Okay, so write down the greatest common factor, 5x cubed. We know there's going to be 3 terms in here. If you want to use the arrows as a guide, as I've been doing, or just think of it mentally, whatever you're comfortable with. But see, instead of division, you could think of it as division. 5 goes into 35 7 times. X cubed divides into x to the fifth, x squared times. I think most people actually think of multiplication. That is, 5 times what is 35, and that's a 7. And then x cubed times what is going to give me x to the fifth. So I need 2 more factors of x. Okay, I'll go to the next term. I'll write down the minus. And ask 5 times what is 25, and that would be 5. And then x cubed times x to the fourth, I need 1 factor of x, so x to the first, or just simply x. And then to the last term, 5x cubed times what is going to give me the 40x cubed. Well, I need a positive and a factor of 8 to get 40. And the x cubed is already there, so I don't need anything else. So correct factorization 5x cubed, and in parentheses 7x squared minus 5x, drop the 1 of course, plus 8. Okay, and as we alluded to earlier, if the leading term is negative, we often desire to factor out the greatest common factor to be a negative. So comparing a negative 3x and a negative 21, 3 is common, but we'll factor out the negative. And then again, reverse the distributive property. Negative 3 times what gives negative 3x. All we need is an x. And negative 3 times what gives negative 21. So that would be a positive 7. So again, recopying the answer. Negative 3 times the binomial x plus 7. Alright, here between each of the terms, again it looks like a 3, but notice the leading term is negative, so I'm going to factor a negative 3. And then also between the variable factors, smallest power is a to the 4th. So we write down our greatest common factor, negative 3, a to the 4th. Okay, now there's going to be 3 terms in parentheses to get negative 9, a to the 6th. Negative 3 times 3 is negative 9. And then we're missing 2 factors of a, so a squared. Go to the next term. Okay, negative 3 times what gives a positive 6? Well, that would be a negative. And a 2. And then a to the 4th times what gives a to the 5th. So we're missing 1 factor of a. So a to the 1st or just simply a. And then to generate the last term, if we'd factor out a negative 3a to the 4th, we're asking negative 3a to the 4th times what gives negative 3a to the 4th, and that would just simply be plus 1. So negative 3a to the 4th, and then 3a squared minus 2a plus 1. Okay, so one more concept, and that's the end of this lesson. And this concept's kind of interesting. You're going to lead to how we can factor some really special polynomials. But here's an idea, just a special example, kind of abstract, but what if I wanted to factor a triangle from x triangle plus 5 triangle? We know the distributive property is a times b plus c gives us a times b plus a times c. And we saw how when we have that common factor of a, we could basically factor it by reversing this distributive property. Well, here the common factor is triangle. So if I pull out a triangle, okay, as a binomial, to get x triangle, triangle times x would give me x triangle, and then plus triangle times 5 would give me 5 triangle. So it's going to be triangle times x plus 5. It doesn't matter what the triangle is. It could be monomial terms like the previous examples, or it could be a binomial term. So, for example, if it could be an abstract term as well. That's why I use triangle. Now, if you look at this example, we have this binomial x minus 6 that's common. So that behaves as the triangle. And we could pull that out. So just write it down, because the greatest common factor is the binomial x minus 6. And then the leftover pieces, you just cover up the x minus 6's. You need a y and you need an 8. So y plus 8. Okay, so in this example now we have the z squared minus 19 as a binomial quantity that is common to both of these terms. And so the greatest common factor is the binomial z squared minus 19. So I would write that down. That's behaving as the triangle. And then upon factorization, okay, to get the first term, you could just cover up the z squared minus 19, and we need an r. And then to get the second term, you could cover it up, and there's just a plus there. But as we know, the coefficient is 1. So therefore we need plus 1. Okay, so the reason why I showed you those concepts is because we have this idea that we call factor by grouping. And it's used when there's 4 terms in the polynomial. Typically when you have a cubic polynomial, so raised to the 3rd power. What you want to do is split the 4 terms into 2 groups of 2. So you kind of split it down the middle. And then factor the greatest common factor from each separately. And then finish factoring like we did in the above examples. So let me recopy x cubed plus 8x squared plus 4x plus 32. And you can even go so far as to draw a little, maybe dotted line there between the 2 groups of 2 terms. Just make sure that the dotted line comes before the addition or subtraction that's in the 3rd term. And then from the first 2 terms, the greatest common factor is x squared. And from the second pair of terms, the greatest common factor is 4. So from x cubed plus 8x squared, I write down the x squared, reverse, there's going to be 2 terms in here. X squared times what gives x cubed, and that's x. X squared times what gives 8x squared, that'd be plus 8. And then here, the greatest common factor is 4. There you want to even go so far as to say positive 4, because you do have to associate a sign with that greatest common factor. And then reversing the process, 4 times what is 4x, just need an x, and 4 times what is 32, and that's plus 8. So let me recopy what we have now. We have x squared times x plus 8, and then plus 4 times the binomial quantity x plus 8. So you can see that now it's just like the previous examples, where x plus 8 is a common factor. We'll write it down. And then the leftovers, basically just cross them out, cover them up, right? Whatever you want. You can see it's x squared plus 4 is what's left over. Okay, so one more to practice here. And this is about as hard as it gets. We get into some other factoring in the next section, but it's a little bit easier. But this has a nice little process to it. So again, I'm going to recopy 16x cubed minus 20x squared, and then plus the 20x minus 25. Draw my little dotted line down the middle, separate two groups of 2, and you don't need to write the greatest common factor down like I'm doing here. I mean, you could jump right to the factorization, but between 16 and 20 I'd need a 4, and between the x cubed and the x squared and x squared, greatest common factor for the second pair with the second group of 2 is just going to be 5. It's common between 20 and 25. Alright, so do the factorizations. 4x squared, and in parentheses we're going to have 2 terms. Get 16x cubed. 4 times 4 is 16. X squared times x is x cubed. And then the 4x squared distributed to give negative 20x squared. We need a negative and a 5. And then we have plus the greatest common factor of 5. Then in parentheses 2 terms. And these problems are basically designed so they work. Notice how when we reverse the distributive, 5 times what gives 20, that's 4. We need an x as well. And then 5 times what gives negative 25, and that would be a negative 5. And notice that these binomials match. So they're kind of designed to work. So we rewrite that binomial that matches. Actually, let me, if you want to take an extra step without all the arrows there, just to see it, 4x squared times the 4x minus 5, and then plus 5 times the 4x minus 5, and again the 4x minus 5 is common. Write it down, and then the leftovers you can just cover them up, and we're left with 4x squared plus 5. Alright, so that's the end of lesson 24, and so we'll see you when you're ready for lesson 25.